It's the only way. Okay, so here we go. I've got here consider the differential equation. That must be a particular solution. I give a differentiation such that the line at y equals -2 is tangent to the graph at f of f. Find the x-coordinate of the point of tangency. Determine whether or not it's a local minimum, local maximum, and neither at this point. Okay, so I've got some sort of funky real. Okay, so remember this is the derivative, right? So I've got some funky real graph. Woo! And somewhere along the line, at y equals -2, I'm going through the point. Now this is a horizontal line, which means the derivative here is 0. So the first thing you notice, derivative with respect to x has to be equal to 0 at whatever this point is. Unfortunately, it doesn't tell us what that point is. We might be thinking, well, okay, how are we going to find that point? Well, look, it has to have a derivative of 0, right? So I could play the game of this has to be equal to 3 minus x over y. We know the bottom can't matter unless it happens to be 0, makes it undefined. We don't want, we're not in a range where well, we might be in a range, we just don't know. Bottom line is the top, in order to make it equal to 0, you have to set this equal to 0, which means x is equal to 3. And so now I take a look at it and go, well, how do I figure whether it's a maximum or minimum, right? I've established the derivative has to be 0. Why? Because the slope of the line is 0. Slope of y equals -2 is 0. So the derivative has to be 0. The only place the derivative is 0 is equal to x equals 3. So since it's x equals 3, I'm going to check to the left and right? So I check a number less than 3. So I check 2. 3 minus 2 over. Now the interesting question, what is y? Is y positive or negative? Because that matters. Let me think. How would I go about that? It says, just like local maximum, local minimum, or neither. Since I don't know whether y is positive or negative, I'm going to have to go maybe second derivative. First derivative test is going to work because I don't have the original function. So the basic derivative test of what's the highest number won't work because I don't have the original function. First derivative test, I can't figure out how to make y with know whether y is positive or negative. It's possible it could be either. Now, to be frank, it's got to be for a short distance, left and right negative, but that makes me a little nervous to say that out loud. Because of that. So I'm a little uncomfortable with it, but I'm going to go ahead and let's try a second derivative test maybe. Second derivative test would take the second derivative, so I'm going to take the second derivative. So let's hope this works better. It may not. Bring up the bottom to the top, so I end up with y times -1 minus, right? I'm doing the quotient rule. So y times -1 times 3 minus x times rid of the bottom, which is the derivative with respect to y, which is 3 minus x, hoping that wouldn't happen, all over y squared. Interesting. All right, what can I do with this mess? Well, does this solve my problem? Yeah, it does. You know why it does? Because I know y has to be negative at the point, right? So for the second derivative test, this is key. So at second derivative test, I know at the point, so y second derivative y at -2 is going to be equal to 2 minus, I got 3 minus x squared, which has to be positive by definition, over -2, all over -2 squared. Now, I don't know much about anything else, but I do know it's going to be 2 plus 3 minus x squared over 2 all over 4. This has to be positive. So since it's positive, this has to be a local maximum, right? Because the second derivative is being negative means it's concave down, which makes this a local maximum. All right. So the second problem is Let y be g of x, a particular solution for the differential equation, -2 from -2 to 8, with the initial condition g of 6 equals -4, y at g of x. Okay, so I want to write an equation that works for all derivatives here. So in order to do that, I'm going to have to take the integral, right? So dy dx equals 3 minus x over y. Separate my variables. I get y dy. Integral equals integral 3 minus x dx. I can do both sides. This is 1/2 y squared plus c. This ends up being 3x minus x squared over 2 plus c. C minus c makes another c. I'm going to solve for it in terms of y. So I'm going to go y squared equals 6x minus x squared minus c. Again, 2 times c is c. Why did I make that a minus? I don't know. It's a plus, but it doesn't actually matter because it became plus and negative. Y equals plus or minus the square root of 6x minus, it's a 6x, minus x squared plus c. So I need to know what makes it work. What's the point they give us? They give us -4, 6. I put a -4 in here. That tells me that this thing here has to be negative, right? So in this particular solution, the plus or minus goes away and only the minus matters. So I get 6 times 6 minus 6 squared plus c. So this whole thing becomes -4 equals negative square root of c. So it doesn't take much imagination, really. That's going to be 16. So my specific equation will be y equals negative square root of 6x minus x squared plus 16. And I think that does it for you. All right. Hopefully that's enough. I will post this, and you'll have